Hey fellow nerds, today we'll solve gate problems on MOSFET circuits from 2019 to 2024. This is our first problem. In the circuit shown, the transistors M1 and M2 are biased in saturation. Their small signal transconductances are GM1 and GM2 respectively. We can neglect the body effect, channel length modulation and intrinsic device capacitances. Also, assume C1 is a short circuit for AC analysis. What we have to find out is the magnitude of the small signal voltage gain V out by V in. I want you to look at just this much of the circuit. What we have inside is a normal common source amplifier. It has a resistor RB, and RB is in series with the MOSFET that is connected like this. So what I'm going to do is to find out the impedance of this extra circuit over here when looked through its gate. Once I find that, I'm going to remove this part and then replace it with a resistor whose resistance will be equal to the equivalent resistance I found. So the first step is to find the equivalent resistance of this much of the circuit when looked through its gate. To do that, we'll first take the small signal model of the MOSFET M1. At the drain of M1, we have a current source. In the small signal model, we'll have to remove it. To remove a current source, we have to open the circuit. So at D, the circuit is open. Another interesting thing we can see here is that the drain and the gate are shorted. So with the small signal model, we'll draw a connection like this. When the drain and gate of a MOSFET are shorted, we can call it a diode connected MOSFET. Now, what we have to find out is the impedance that we see when we look through the gate. To find that, I have to apply a potential Vx over here at the gate in the small signal model and find its relation with Ix, which will be the current flowing over here. First thing you can see is Vx is directly connected across gain and the source. That means VGS1 is equal to Vx. Also, current Ix flows like this and then it flows like this because the circuit is open over here. That means Ix is equal to GM1 VGS1. But VGS1 is Vx. So we get Ix is GM1 Vx, or Vx by Ix is just 1 by GM1. So this much of the circuit can be modeled as a resistor whose resistance is simply the inverse of the transconductance of MOSFET 1. Now, with that idea, let us draw the small signal model of the common source amplifier. For that, I will take the small signal model of MOSFET number 2. Output is taken at the drain. We have a resistor at the drain. In the small signal model, it will be connected between the drain and the AC ground. Capacitor C1 will be shorted in the small signal model. We will have Rs and Vin in series connected to the gate. Finally, we have a resistor Rb, and in series to it, we will have another resistor 1 by Gm. Let us show them in the small signal model. At the output, we can see GMVGS2 is flowing in this direction. So it must have come through RD like this. If the current flowed through RD from this point to this point, that means RD must have a positive potential here and negative here. But we are taking Vout from this terminal. So Vout will be negative of the potential drop across RD due to the current GMVGS2. So according to Ohm's law, Vout will be negative of current flowing through the resistor multiplied by the resistance. At the gate, we have Rb and 1 by Gm1 in series. To make it simpler, let us model them as one resistor whose resistance is Rb plus 1 by Gm1. You can see that this resistor is directly connected across the gate and the source. That means the potential across Rb plus 1 by Gm1 is equal to VGS2. Now, if you take a look at this loop, you can see Vin is being divided between Rs and Rb plus 1 by Gm1. So the potential drop across RB plus 1 by GM1 can be calculated simply by using voltage division, and that will be equal to VGS2. So Vin is being divided between Rs and Rb plus 1 by Gm1. Whatever gets dropped across Rb plus 1 by Gm1 will be equal to VGS2. So we can write VGS2 is Vin divided by Rs plus Rb plus 1 by Gm1 multiplied by Rb plus 1 by Gm1. Let us replace the VGS2 over here in this equation with what we found over here. Then we get Vout is minus Gm2 Rd multiplied by Vin divided by Rs plus Rb plus 1 by Gm1 multiplied by Rb plus 1 by Gm1. What we want is the voltage gain Vout divided by Vin. We have Vout here, we have Vin here. So simply by taking Vin to the other side of the equation, we get Vout by Vin. And it is negative Gm2Rd multiplied by Rb plus 1 by Gm1 divided by Rb plus 1 by Gm1 plus Rs. The question is only to find the magnitude of the gain, so option B will be the right answer. So when you see a diode connected model in the circuit, know that you can model it as a resistor whose resistance is the reciprocal of the transconductance of that MOSFET. Let us solve the next problem. In the circuit, assume that the long channel NMOS transistor is biased in saturation. The small signal transconductance of the transistor is Gm. We can neglect body effect, channel length modulation and intrinsic device capacitances. What we have to find out is the small signal input impedance Zn as a function of j omega. From the figure, we can see that Zn is the input impedance we see when we look through the gate. Let's figure this out. The first thing we need, as always, is the small signal model of the MOSFET. Drain is grounded. From the source to the ground, we have a capacitance. Its capacitive reactance will be 1 by j omega Cl. So to model it, let's put an impedance over here, which is equal to 1 by j omega Cl from the source to the ground. The same way, we have this capacitance C1. It is between the gate and the source. So between the gate and the source, we'll put an impedance whose value is 1 by j omega C1. I'm calling this one ZL and this one Z1. What we want to find out is the input impedance as a function of j omega when we look through the gate. So to do that, I have to connect a potential Vx at the gate and find its relation with Ix, which will be the current flowing into the gate like this. Now current Ix flows through Z1 like this. So the potential drop across Z1 is Ix multiplied by Z1. But the potential drop across Z1 is also VGS. So we can write VGS is Ix multiplied by Z1. Now consider the source terminal. Current Ix will flow into it. Current GMVGS also flows into it. Both of them together will flow through ZL. So the current that will flow through ZL is Ix plus GMVGS. Current will be flowing in this direction. So ZL will have a potential drop across it, which is equal to sum of Ix and GMVGS multiplied by ZL. Positive potential here and negative here because current is in this direction. Now let us apply Kirchhoff's voltage law in the gate source loop. I'll start from this point and go clockwise. First I have Vx from negative to positive. As I go on, I have VGS, which is the potential across Z1 from positive to negative. Further as I go on, I have the potential drop across ZL, which is equal to Vs. Then I go back to ground. So I can write Vx minus VGS minus Vs is equal to 0. Now VGS is IXZ1. Vs is Ix plus GMVGS ZL. Let us replace both of them. This is what we get. Let us take these two terms to the other side of the equation. So these two negatives will become positive. Here again we have a VGS. Let us replace it with Ix Z1. in this term, if we open the bracket, we get Ix multiplied by ZL plus GM Ix Z1 multiplied by ZL. Now all these terms have Ix in common. So we can write it as Ix multiplied by Z1 plus ZL plus GM Z1 ZL. What we want is Vx by Ix. From this equation, we can easily write that. Vx by Ix is Z1 plus ZL plus GM Z1 ZL. Z1 is 1 by j omega C1. ZL is 1 by j omega CL. So if we write them that way, this is what we get. In the third term, we have 1 by j omega C1 multiplied by 1 by j omega C2. J multiplied by j is j square, which is minus 1. Omega multiplied by omega will become omega square. So this whole thing can be written as negative 1 by omega square C1 C2. So Vx by Ix is 1 by j omega C1 plus 1 by j omega C2 minus Gm divided by omega square C1 C2. Option A is correct. Let us see the next problem. Circuit shown has an ideal long channel nMOSFET. It is of enhancement mode. Substrate is connected to the source. All the basic things. The transistor is approximately biased in the saturation region with VGG and VDD such that it acts as a linear amplifier. Vi is the small signal input voltage. Va and Vb represent the small signal voltages at the nodes A and B respectively. From the figure we can see A is just the drain and B is the source. Now what we have to find out is the value of Va by Vb, rounded off to 1 decimal place. So the first thing we need to solve this problem is the small signal model. Let us start by taking the small signal model of a MOSFET. VGG and VDD will get shorted. V input is connected at the gate. The 4 kilo ohm resistor in the small signal model will be between the drain and the AC ground. The 2 kilo ohm resistor will be between the source and the AC ground. Now A is taken from the ground, so we can mark this point over here as A. B is taken from the source, so let us mark it over here. According to the problem, potential at A is VA and potential at B is VB. We can see that GMVGS flows in this direction. So it must have flowed through the 4 kilo ohm like this. In that case, the potential across the 4 kilo ohm should be positive here and negative here. Now VA is taken across the 4 kilo ohm. But there is a problem. VA is taken from the negative potential. So VA will be negative of whatever is the potential dropped across the 4 kilo ohm due to GMVGS flowing through it. So VA is negative of GMVGS multiplied by 4 kilo ohm. How about VB? VB is taken across the 2 kilo ohm. What is the current through 2 kilo ohm? You can see that GMVGS flows like this and then it flows through the 2 kilo ohm. It is flowing in this direction. That means the 2 kilo ohm has a positive potential here and negative here. So VB is equal to the potential dropped across 2 kilo ohm due to GMVGS flowing through it. So VB is GMVGS multiplied by 2 kilo ohm. What we want is VA by VB. From here we can easily see it is minus 4 by 2, which is minus 2. So the final answer is minus 2. There's actually another way of solving this problem. Here the input is given at the gate. If you consider that the output is taken at the drain, then this will be a common source amplifier. VA by Vin will be the gain of a common source amplifier. Now, gain of a common source amplifier with RD and RS is minus RD divided by RS plus 1 by GA. The same way, if you consider input is given at the gate, output is taken at the source, then it will be a common drain amplifier. VB by Vin will be the gain of a common drain amplifier. For a common drain amplifier, gain is given as RS by RS plus 1 by GA. Now, to get the ratio VA by VB, all you have to do is divide this with this. To do that, we can multiply VA by Vin with Vin by VB. If we do that, RS plus 1 by GM and RS plus 1 by GM will get cancelled and we get minus RD by RS. RD here is 4 kilo ohm, RS is 2 kilo ohm. So again, we get VA by VB is minus 2. Let us see the next problem. We have an ideal long channel enhancement mode nMOSFET with gate length 10 micrometer and width 100 micrometer. The product of electron mobility and oxide capacitance per area, that is µnCox, is 1 milliampere per volt square. Threshold voltage of the transistor is 1 volt. The gate to source voltage VGS is 2 minus sine of 2t volt. The drain to source voltage VDS is 1 volt. Substrate is connected to the source. What we have to find out is the maximum value of the drain to source current. The question is to find the maximum value of the drain current. So the natural instinct is to use the equation µnCox W by L VGS minus VTH whole square. But before we jump into that, we have to make sure in which region the MOSFET is working in. So let us do that first. It is given that VGS is 2 minus sine of 2t, which means VGS is a sinusoidal voltage with a DC voltage added to it. We know drain current increases with VGS. That means drain current will be maximum when VGS is maximum. Here VGS is 2 minus sine of 2t. It will be maximum when sine of 2t becomes minus 1, making VGS 2 minus minus 1, which is 3 volt. In the question it is given threshold voltage is 1 volt. So since the maximum value of VGS is 3 volt, maximum value of VGS minus VTH will be 3 minus 1 or 2 volt. It is also given that VDS is 1 volt. So VDS is less than VGS minus VTH, which means the transistor is not operating in saturation region. Instead, it is in the triode or linear region. In the linear region, the equation for drain current is µnCox W by L VGS minus VTH multiplied by VDS minus VDS square by 2. To get the maximum current, we have to take the maximum value of VGS minus VTH. We have all the values required. µnCox is given. W by L can be found because L is given, W is also given. VGS minus VTH, its maximum value is 2 volt. VDS is 1. So all we have to do is give values. That gives us maximum value of the current is 15 milliampere. Option C is the correct answer. Let us see the next problem. We have ideal long channel nMOSFET and pMOSFET shown in the figure. Their threshold voltages are 1 volt and minus 1 volt respectively. The MOSFET substrates are connected to their sources. We can ignore the leakage currents. Assume that the capacitors are initially discharged. For the applied voltages shown in the figure, we have to calculate the steady state voltages. That means, if you take the nMOSFET, 5 volt is given over here, 5 volt is given over here, we have to find the steady state voltage V1. For the pMOSFET, minus 5 volt is given here, 5 volt is given here, we have to find the steady state value of V2. Now the first and the most important question to ask here is which one is the drain and which one is the source? Because in both these figures, source and drain are not marked. It is obvious that this is the gate terminal, but which one is the source and which one is the drain? That is the first thing we have to find out. So let us do that. I'll take the nMOSFET first. I am calling this terminal A and this terminal B. Let us start by finding the source and the drain. The maximum potential we have anywhere in this circuit is 5 volt. The minimum we have is 0 at the ground. So the potential V1 cannot be greater than 5 volt. It cannot be lesser than 0 volt. So V1 has to be between 0 and 5. That means V1 is always going to be less than or equal to the potential at A. For an nMOSFET, we always give positive potential to the drain with respect to the source. So A has to be the drain and B has to be the source. That means current will flow from the drain to the source like this. This current will charge the capacitor. So the capacitor will get a positive potential here and negative here. But there is one condition for the current to flow, right? The MOSFET has to be switched on. So to be more correct, we have to say current flows from the drain to the source and the capacitance charges as long as the MOSFET is on. That means now we have to figure out the condition for the MOSFET to be on. The condition for an nMOSFET to be on is that VGS should be greater than or equal to the threshold voltage. Now VGS can be written as VG minus VS. Here VG is 5 volt. Vs is what we have to find out, V1. Vt is given in the question, it is 1 volt. So we can write 5 minus V1 should be greater than or equal to 1, or V1 should be less than or equal to 4. What happens if V1 is greater than 4? Then the MOSFET will switch off. So the maximum value V1 can have is 4 volt. What is the minimum value it can have? We started by saying V1 can only take values between 5 and 0. But now we learned V1 also has to be less than or equal to 4. So technically V1 can only take values from 0 up to 4. If it is between 4 and 5, then the MOSFET will be switched off. It is given in the question that the capacitor is initially discharged. So initially it does not have any potential across it. So V1 starts with 0. When V1 is 0, obviously the MOSFET is on. So current will flow from the drain to the source and that will charge the capacitor and the potential will increase. So potential starts increasing from 0. At some point it will reach 4 volt. After that it cannot increase anymore because the MOSFET will switch off. So the steady state voltage across the capacitor is 4 volt. Let us take the pMOSFET now. Again I have marked this terminal as A and this one as B. Just like we did with the nMOSFET, we have to find out which one is the source and which one is the drain. Let us take a look at the circuit. The lowest potential we can see is minus 5. The highest potential is plus 5. So V2 cannot be lesser than minus 5. It cannot be greater than 5. So V2 has to be between 5 and minus 5. Here terminal A has a constant potential V. V2 can only take values from minus 5 up to 5. That means V2 is always less than 5 volt. V2 is always less than VA. For a pMOSFET, we connect a more negative potential at the drain than the source. So here B has to be the drain, A has to be the source. Again, in a pMOSFET, drain current flows from the source to the drain. So here the current will flow in this direction and charge the capacitor. So here also the capacitor will get positive potential here and negative here. But there is a condition for current to flow, right? The MOSFET has to be switched on. So to be more correct, we have to say current flows from the source to the drain and the capacitance charges as long as MOSFET is on. So the next thing we have to do is find the condition for the pMOSFET to be on. What we have here is a pMOSFET. Condition for a pMOSFET to be switched on is that VSG should be greater than or equal to magnitude of the threshold voltage. Threshold voltage of a pMOSFET is negative. We only have to take the magnitude of it. Now VSG can be written as Vs minus Vg. Vs is 5 volt, Vg is minus 5 volt. So we get 5 plus 5 or 10 volt, which is greater than the magnitude of threshold voltage. Because according to the question, threshold voltage is minus 1 volt. Its magnitude is 1 volt. 10 volt is very much greater than that. Here the source voltage is fixed at 5 volt. Gate voltage is also fixed at minus 5 volt. So Vs minus Vg is always going to be 10 volt. It is always going to be greater than the magnitude of the threshold voltage. Does that mean this MOSFET is always going to be switched on? That's exactly what it means. This MOSFET is always switched on. So the current will flow as long as the capacitor gets completely charged. How do we know the capacitor gets completely charged? It is given in the question, capacitor is initially discharged. So we can say initially it doesn't have any potential across it. So what we have over here is 0 volt. So current will flow from the source like this and charge the capacitor. So potential across the capacitor increases from 0 volt. At some point it will become 5 volt. Then what happens? Then at the drain we have 5 volt. At the source also we have 5 volt. That means the drain source voltage is 0. That will make the drain current 0. That's when we say the steady state has reached. So at steady state, capacitor is completely charged and the drain current will stop. ID becomes 0. Why does ID become 0? Because VDS is now 0. That means Vs is equal to Vd. Here Vs is 5 volt, Vd is V2 whose steady state value we have to find out. So Vs or V2 is 5 volt. Now you don't have to go through the entire thought process every time you see a problem like this. I'll teach you a trick. In the case of pMOSFET, we started by saying V2 can only take values between 5 and minus 5. Here, the MOSFET is always on. So V2 took the maximum possible value 5 volt. In the case of nMOSFET, we said V1 can only take values between 5 and 0. V1 could have taken 5 volt, but it couldn't. Why? Because after 4 volt the MOSFET switches off. So it could only take up to 4 volt. So you can see it this way. If the MOSFET is always on, in both cases output will be equal to input. Otherwise, we'll have to check the condition for which the MOSFET will be on. In the case of an nMOSFET, the condition is that VGS should be greater than or equal to the threshold voltage. Or we can write VG minus Vs is greater than or equal to threshold voltage. That means source voltage should always be less than or equal to Vg minus Vt. So if the MOSFET is always on, output will be equal to input. But if Vg minus Vt is less than the input, then that will be the output. That means V output is the minimum of V input and Vg minus Vt. Similarly, the condition for a pMOSFET to be on is that VGS should be less than or equal to V threshold. Over here, I have written VGS should be greater than or equal to magnitude of V threshold. Magnitude of V threshold is actually negative of V threshold. That is why here it is greater than or equal to, and here I am taking less than or equal to. Now, VGS is less than or equal to V threshold means Vg minus Vs is less than or equal to V threshold. Or we can say Vs is greater than or equal to Vg minus Vt. So if MOSFET is always on, output will be equal to input. But if Vg minus Vt is the greater value, then that will be the output. So here we can say V output is the maximum between V input and Vg minus Vt. So to solve this problem, all you have to know is this. For the nMOSFET, steady state value of V1 will be minimum of Vg minus Vt and Vin. Here Vg is 5, Vt is 1. So Vg minus Vt will be 4. Vin is 5. So the minimum of 4 and 5 is 4 volt. For the pMOSFET, it is the maximum between Vg minus Vt and Vin. Here Vg is minus 5. Vg minus Vt will be minus 5 minus minus 1. That is minus 4. So we have to take the maximum value between minus 4 and minus 5, which is 5 volt. Option C is the correct answer. Let us see the next problem. We have a CMOS circuit shown in the figure. Substrates are connected to their respective sources. The ratios W by L of the transistors are given in the figure. Both transistors have the same gate oxide capacitance per unit area. For the pMOSFET, the threshold voltage is -1 volt. Mobility of holes is 40 centimeter square per volt second. For the nMOSFET, the threshold voltage is 1 volt and the mobility of electrons is 300 centimeter square per volt second. What we have to find out is the steady state output voltage V0. Let us find that. The first thing you have to notice in the circuit is this. For both MOSFETs, gate and drain are shorted. You can see that for the pMOSFET and also for the nMOSFET. Now, what is the significance of drain and gate being shorted? VD will become equal to VG. That means VDS, which is the voltage of the drain with respect to the source, will be equal to VGS, which is the voltage of the gain with respect to the source. That means VDS will always be greater than or equal to VGS minus VTH, which means the MOSFETs are always going to be in saturation. Let it be there. Let us take a look at the pMOSFET. In a pMOSFET, drain current flows from the source to the drain. So it will flow like this. I'll call that current ID1. For the nMOSFET, current flows from drain to source. So it will flow like this. I'll call it ID2. But with a better look, we can see that ID1 is actually the same as ID2. So let us write ID1 is equal to ID2. How do we express ID1 and ID2? We saw that the MOSFETs are in saturation. So current will be maximum. Maximum value of drain current is given by µnCox W by L VGS minus VTH whole square. At least for nMOSFET that is. For pMOSFET we have to write mu P Cox W by L1 VSG1 minus magnitude of VTH1 whole square. This will be equal to mu n Cox W by L2 VGS2 minus VTH2 whole square. We have all the values required. Mu P and mu n are given in the question. It is also given that Cox is the same for both of the MOSFETs. W by L for the first one is 5. For the second one, it is 1. Magnitude of VTH is 1 for both of them. Now, what is VSG1? VSG is Vs minus Vg. For the first MOSFET, source voltage is 4 volt. Gate voltage is V0. So VSG is 4 minus V0. The same way, what is VGS2? VGS is Vg minus Vs. For the second MOSFET, gate voltage is V0. Source voltage is 0. So Vg minus Vs or VGS2 is V0. So we can write it this way. Cox and Cox can be cancelled. Here we have 40 multiplied by 5. Here we have 300. That can be simplified. 4 minus V0 minus 1 can be written as 3 minus V0. If we do that, we get 2 times 3 minus V0 whole square is 3 times V0 minus 1 whole square. All we have to do is do some simplification and we get this quadratic equation. V0 square plus 6V0 minus 15 is equal to 0. To find the value of V0, we can do this. V0 is negative B plus or minus root of B square minus 4AC divided by 2A. That gives us two possible values of V0. They are 1.898 volt and minus 7.98 volt. Which one can be the correct answer? From the circuit we can see that the maximum voltage we give is 4 volt. The minimum voltage that there is 0 volt. So the output has to be between 4 and 0. So minus 7.89 is not possible. The correct answer is 1.898 volt. It is less than 2 volt, so option C is the correct answer. Let us see the next problem. Using the incremental low frequency small signal model of the MOS device, we have to find the Norton equivalent resistance of the following circuit. Norton equivalent resistance is the same as Thevenin equivalent resistance. So technically, all you have to find here is the impedance you see when you look through the source. In the figure, as the properties of the MOSFET, GM and RDS are given. RDS is here, which means channel length modulation is included. Now, the first thing we need to find the impedance is the small signal model of a MOSFET. Gate is grounded. RDS has to be connected between the drain and the source. R has to be connected between the drain and the AC ground. Now, what I have to find out is the impedance when I look through the source. So I have to connect Vx at the source and find its relation with Ix, which will be the current flowing over here. If you take a look at this node, Ix is flowing into it. GMVGS is also flowing into it. So the current that flows through here and further flows through RDS will be Ix plus GMVGS. Now see this node. Ix plus GMVGS is flowing into the node. Out of that, GMVGS is flowing out of the node. That means whatever is left, which is Ix, will flow like this through R. First, let us apply KVL in this loop. Vx goes from negative to positive. VGS is from negative to positive. So we can write Vx plus VGS is equal to 0, or Vx is the negative of VGS. Now let us apply KVL in this loop. I'll start from this point and go clockwise. First I have Vx from negative to positive. As I go on, I have the potential drop across RDS. RDS has a current Ix plus GMVGS flowing through it. It is flowing in this direction, so we have positive here and negative here. Potential will be Ix plus GMVGS multiplied by RDS. As we further go on, we have the resistor R, through which Ix is flowing in this direction. So it has positive potential here and negative here. The potential drop will be Ix multiplied by R. Now, Vx is from negative to positive. Potential drop across RDS is from positive to negative. Potential drop across R is also from positive to negative. So we can write Vx minus Ix plus GMVGS multiplied by RDS minus IXR is equal to 0. Now, we know VGS is minus Vx. So over here, instead of VGS, let us write minus Vx. Let us open this bracket so that we get minus IXRDS plus GMVXRDS. Let us take all the terms with Vx in it on the left hand side and all the terms with Ix in it on the right hand side. This is what we get. Vx multiplied by 1 minus GMRDS is equal to Ix multiplied by RDS plus R. What we have to find out is Vx by Ix, which obviously is from RDS plus R divided by 1 plus GMRS. Option B is correct. So that's all about it for today. See you in the next video. And please don't forget to subscribe.